let's take an example now of an indexed family of sets. Let's let capital B subscript n be the interval, the open interval from 0 to 1 over n for all natural numbers n. So I guess technically we've just defined the indexed family of sets like this. When you use a set here, it just represents that I've defined a set B for every natural number n, B1, B2, B3, and so on. So that's what we have here. We have an indexed family of sets. Let's take a look at the union of all of those Bn's for all little n in the natural numbers. This is two separate ways of writing it, and I interchange them. You can say the union of the Bn's where n equals 1 to infinity, or you can simply say that n for all the natural numbers. N is a natural number, the union of the Bn's. Well, when n is a 1, we get 0, comma, 1 over 1. The next one would be the second set, b sub 2, which would be 0, comma, 1 half, union 0, comma, 1 third, union dot, 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 and it goes on forever. So what do you think that would be equal to? Well, notice each set in this list that's being union is a subset of the previous set. So if I do 0, 1, and I say union that with 0, comma, 1 half, that's like taking this interval and then unioning it with that interval. It gave you nothing extra. Okay, so it should be easy to see then, since every set is a subset of the previous set, that this is just equal to the interval from 0 to 1. There's none of these intervals from here on finds any number in it outside of 0 to 1. All right, now let's look at the intersections. So we've got 0, comma, 1 intersected with 0, comma, 1 half, intersected with 0, comma, 1 third, intersected, and so on, forever. We're looking for the intersection. We're looking for the number or numbers that are in this set, and this set, and this set. So pick a number that's in all of them. So the difference is now we start off with this, but the second set goes from 0 to 1 half. When we intersect those two, the only thing they have in common is this. And then when I intersect that with a smaller set, 1 third, the intersection of all these three sets is just this one. And notice it's shrinking smaller and smaller. So hopefully it's easy to see that there's no element that's in all of those sets. Okay, let's do a simple proof of this one. Proof of B. I'm going to do what's called a proof by contradiction. We're going to start off by saying to the contrary. Suppose some number x is in the intersection of all of those Bn's. Okay, well, I'm going to choose some natural number in such a way that this number is bigger than the reciprocal of x. If x is a small number, 1 over x is a big number. And I'll go ahead and say that is x is bigger than 1 over m. Those two things just mean the same thing. Well, since x is not in the interval 0 to 1 over m, and why is that? Because this is the numbers between 0 and 1 over m, and x is greater than 1 over m. We see that x is not an element of b sub m. Because b sub m, by definition, is the interval from 0 to 1 over m. This is 0 to 1 over 1, 0 to 1 over 2, 0 to 1 over 3, and so on. Now I'm going to put a comma there instead of a period. If it's not in bm, that means b sub m, that means that x is not in the intersection of the bm's. Because we found one of the sets that it's not a member of. And in fact, that means if it's not in 1 over m, then it's not in, if you take 1 over 2m or 1 over 3m, shrinking this interval, it's also not in those. So this is a contradiction, because to the contrary, we supposed that x was in the intersection. That means it's in every single one of the b's. It's in b1, b2, b3, bm, bm plus 1, and on forever. We assume that to be true here. Since assuming that, we found a contradiction. It's not in this one. That contradiction proves that what we assumed, that's false. That contradiction, so we can say, therefore, there is no x in the intersection, which means the intersection of the bn's is in fact equal to the empty set. And by the way, we used something here that we may all take for granted, but we use a little something called the Archimedean property. I'm going to write it down and then erase it. Almost done, and I need this board for the next problem. The Archimedean property for the ordered field R. I'll define what an ordered field is later, but R is an ordered field, the real numbers. We'll get to that in the next section, but what it says is, for every x and y in the real numbers, there exists an n, I'll call it a lowercase n, in the natural numbers such that nx is greater than y. I'm not going to make you recite that on an exam or anything like that, but we use the Archimedean principle in this area right here. And again, we'll discuss at least the ordered field R in the next section. Okay, to finish up this entire section, I'm going to write down theorem 0.4, which will look quite familiar. I'm going to call it the generalized De Morgan's laws. So we're using more than just one set. It'll look very similar to something we've seen already. Let A sub lambda, for all lambdas in capital lambda, be an indexed family. I'm not just going to say of any sets, but of subsets of the set capital S. So every one of these A sub lambdas is a subset of capital S. The generalized De Morgan's laws say that S minus the union of the A lambdas is equal to the intersection of the S minus A lambdas. And if you think hard on that, it's pretty similar to something we've looked at earlier. And the second one will be flipping unions and intersections upside down. So it's very similar to De Morgan's laws. The only difference is that these are subsets of some S. So in De Morgan's law, our S is really the universal set. The old De Morgan's law would say something like the union of the AI's. I'm just going to use I for the index, and maybe I goes from 1 to infinity. If you take the complement of that, you get the intersection of that. That would be one of De Morgan's laws, and the other one would look like this. If you take the intersection of all the sets, and then take the complement, you're going to get the union of the individual complements. This is kind of the original De Morgan's law for more than 2 sets. And that finishes off section 0.1.